this method called the Lagrange Equation. And this is an alternative method for deriving the equations of motion in any mechanical system. And this method is kind of like energy methods. It is typically, when the system gets more and more complicated, this method has advantages over the Newton's method. Because first of all, you're not dealing with vectors, you're dealing with energy, which is a scalar. And now tell you it's not perfectly energy, there is force in it involved as well, so I cannot completely call it the energy method, but it is similar to the energy method. And the main advantage of this method, as I mentioned at the very end of this PDF, is when you go with this method, many of the reaction forces that are unknown, you skip calculating them. So you end up with fewer equations and fewer unknowns to solve for. So that's why in systems that are complicated, they have too many degrees of freedom to find the equation of motion for them. You don't want to add a lot more reaction forces on the top of those variables and make your system of equations, which are typically nonlinear, a lot bigger. So this method has that advantage, and I'll show you. But and it is derived from the Newton's equations plus the D'Alembert's principle. And the text here that I chose for you from a dynamics textbook, basically, which I guess you can see it here, or let me see if I can find the name of the book for you. I'm not sure if it's shown here or not, but I'll put the name of the book for you as well here. But this is a little bit heavy to understand, okay? So the language of that is a little bit beyond the elementary dynamics course that you guys are having at the moment. This is typically what is taught in advanced dynamics courses, which are graduate level courses. So this derivation here is starting from the D'Alembert's principle, using the external forces and the basically we call them inertial forces, Fi star, and the virtual displacement when you freeze the time and everything. So it might be, as I said, a little bit beyond the level of this course. So I'm not going to go through all of this derivation and all of these partial derivatives and everything. And I'll tell you the endpoint of it, which is the Lagrange equation. So this is the Lagrange's equation, this one. And without me even directly diving into this equation and using it, I'll try to kind of derive it for you in a simpler manner and make life a little bit easier for you to understand it a little bit better with a couple of examples first, and then I'll come back to this equation, explain the meaning of every term, L, Qi, small cap Qi, and so on, okay? So as I said, this is a second method, an alternative method to derive the equations of motion. And you might even call it not the second method, the fourth method, because we had Newton's method, we had work energy principle, we had impulse and momentum, and now this is a fourth method. It's called the Lagrange's method. So let me show you first the Lagrange's method, and there are two examples in this 6-page PDF file. One is a single pendulum, the other one is a double pendulum. But I'll use another example, not in this PDF, and that's our familiar example of what? Mass spring system. So let's go over that, and then I relate that to these equations. So if we want to derive the equation of motion for the mass spring system, without any external forces for the moment. Okay, so let's say this is the mass spring system, K, M, this is X, and no external force, no friction here. It's just rolling friction, which is not going to affect the equation of motion. At least we don't consider it in this course, as I said. So, you know, from the Newton's second law, we say that mx double dot, correct, is equal to negative kx. Or we can, if we bring it to the right-hand side, bring it to the left side, we can write it as mx double dot plus kx equals 0. Now, if you don't mind, instead of mx double dot, I write the original second law of Newton. Remember, the original second law of Newton does not say mass times acceleration is sum of the external forces. It says what, if you remember? It says rate of change of what? Linear momentum with respect to time is sum of the external forces. And I bring this kx to this side. So I write it like this, if you don't mind. Okay, and here we assume that this m is constant, so d over dt of mx dot is going to be mx double dot. Right, so I can write it this way. And again, this guy is what I call the momentum. Right? Good. So, now let me do a little bit more manipulation here. So if you don't mind, again, if I ask you in this example here, what is the kinetic energy? And to not confuse the kinetic energy with the spring constant, I use T for kinetic energy, if you don't mind. In this text here, you see T is used for kinetic energy, so I use the same notation. So T here, kinetic energy of this object in general is what? You know it. It is 1/2 mx dot squared. Agreed? Yes, and if I ask you what is the potential energy of this system at any arbitrary point, you say it's what? 1/2 kx squared. Correct? So these are the potential and kinetic energy for this system. Now, if I ask you, form this new quantity L, is called Lagrangian, which is kinetic energy minus potential energy for this system. You say it is 1/2 mx dot squared minus 1/2 kx squared. Correct? So this is the Lagrangian for this system. And then if I ask you, you see the Lagrangian is a function of what? Velocity and position. If I ask you, what is the partial derivative of Lagrangian with respect to the velocity term, what would you say? Right, you only have to take care of this term. So 2 and 2 with 1/2 cancels, so you will get mx dot. And this term does not have any x dot, so that's it. And if I ask you what is the partial derivative of L with respect to x, the other variable, you say negative kx. Agree? So now I want you to basically write this like this. I would say this is minus kx equals 0. Right? You can write it this way. Now, what is mx dot from here? Mx dot is partial derivative of Lagrangian with respect to x dot, so I write it like that. Minus, what is negative kx? It is partial derivative of Lagrangian with respect to x. So you write it like that. Equals 0. So the second law of Newton, that was this guy here, I can rewrite it also in this format. I can write it like this. for this system, for the mass spring system, if I use this equation where L is kinetic energy minus potential energy, we call it Lagrangian. If I plug in that L into that equation and perform the derivative here, time derivative, and the partial derivatives, I would get back my second law of Newton. So these two are equivalent to each other. Whether I use this one or this one with the L defined that way, they are both giving me the equation of motion. So this new formulation of the equation of motion is what I call Lagrangian. Okay, Lagrangian and Lagrange method. So this is the Lagrange method, and this L is what we call Lagrangian. Okay, so I can write it this way. So I found an alternative derivation for the case of mass spring system. But you might say, well, that was one example. If you change the system, add more components to the system, or change it to another system, can you still use this formula that you just found, this equation that you just found? Can you still use it? And the answer is yes. And that's what all this PDF file is saying, all the way from page 1 to basically end of page 3. So it is showing that this equation is valid for any arbitrary system. Now, let me add a little bit more to it because there is a right-hand side. So I'll talk a little bit more about that. And then, as I said, we come back to this general form and we'll talk more about it. So if I go back here and I add a damper to the system. So I come here and I add a damper. If I do that, now I have a negative Cx dot term as well. And if I bring it to the right hand, or if I just keep it on the left right hand side, this is going to be negative Cx dot. So my equation is now like that. So this guy should now be negative Cx dot. And you might say, well, negative Cx dot does not have anything to do with kinetic energy or potential energy, right? The potential energy is due to spring, the kinetic energy is due to velocity of the particle and mass. So what is this damper term? How can we represent that in relation to Lagrangian? And the answer is you don't. But this is an external force and non-conservative. Remember, we have conservative forces and non-conservative. Friction is a non-conservative force. This is a non-conservative force acting on this particle that is not included in Lagrangian. So if you really want to include that negative Cx dot, you have to say, basically, instead of saying this is equal to 0, you have to say this is equal to what? This is equal to the Q non-conservative. And the non-conservative force on this object is negative Cx dot. So if you write it this way, now it's more complete because it can include forces that are non-conservative forces. If a force is conservative, it will show itself in what? In the potential energy. It will show itself here. The partial derivative of the potential energy with respect to x is negative kx. Okay, so it shows itself. But if it's non-conservative, it's not going to show itself in any of these derivatives. So you have to take it to the right-hand side. Okay, so that's what it is. And if you use this form, now it can include the damper. And you might say, well, what if I have another external force here, F of t here? Well, you know this F of t is also non-conservative. So if you have to add it here on the right-hand side, then this Q non-conservative is sum of the two, right? All of the non-conservative forces acting on the particle or the object. So again, it is valid. And you can show that this formula is valid for any arbitrary system. Another way to interpret this formula is this. As I said, The second law of Newton says what? It says d over dt of momentum of the system, P, correct, is equal to sum of the forces. Correct? That is the second law of Newton. Now here, this is what we do. We say the sum of the forces is equal to the conservative forces and the non-conservative forces. So now the non-conservatives, you keep it as is. The conservatives, you try to relate them to potential energy, and the momentum you try to relate to what? Kinetic energy. You say, well, the kinetic energy, T, is what? What's the kinetic energy? Kinetic energy is 1/2 mv squared, right? Or if you want, you can multiply it by m and divide it by m, so it is going to be 1/2m mv squared. You can write it this way, and this mv is p, so it is p squared over 2m. Okay, yes? So now, if you take the partial derivative of the kinetic energy with respect to the momentum p, correct? But not just momentum p, with respect to momentum p divided by m. Okay, so basically like this. Let me write it this way. So this p over m is the velocity. If you take partial derivative of the kinetic energy with respect to the velocity, since this m we assume constant, it comes out and it comes to the numerator, so it is going to be m partial derivative of t with respect to p, and then you can see based on here, partial derivative of t with respect to p is 2, and 2 would cancel. You're going to get p over m, so it is going to be m times p over m, so it is going to be p. Okay, so this guy here is, instead of that, you can write it as partial derivative of t with respect to p over m. And actually, even if I subtract potential energy from this, so basically, since the potential energy is never a function of velocity, or at least we assume that it is not a function of velocity, then this, instead of partial derivative of t with respect to p over m, I can write it partial derivative of L with respect to p over m, right? Because again, we assume here, and we say it in the, you'll see it in the PDF, we assume that the potential energy of the system, so L, which is t minus v, this t is a function of velocity, but this potential energy is not. It is only a function of position. Okay, it is only a function of position, not velocity. And again, if you go down and look at the assumptions when this method was derived, you can see that the potential energy V is only the function of the generalized coordinates, the variable, the position, not the velocity q dot. Okay, so this is one of the important assumptions. If there is a system where potential energy is a function of velocity, then this method cannot be used. So here, again, since this is only a function of positions, like in this case x, and not x dot, then I can say when I take partial derivative of L with respect to x dot, that's the same as partial derivative of only t with respect to x dot. because v is not a function of x dot. And x dot is what? X dot is this guy here, p over m. So this is x dot. Now in the notation of Lagrangian method, instead of x dot, I call it q dot. Okay, that's the same thing. A little bit more general, we call it generalized coordinate, and I'll talk about it. So instead of t, I can write it as L, and instead of p over m, I can write it as what? Right, q dot, or x dot. And these conservative forces, I can easily show that conservative forces are the partial derivative of potential energy with respect to the position. That's the definition of actually potential energy, right? That's the definition of potential energy, or that's the definition of a conservative force. If you remember, when we talked about conservative and non-conservative forces back in the work energy principle chapter, I told you that conservative forces are what? Are negative of the derivative of the potential energy with respect to the position, right? With respect to that coordinates that here we call q instead of x. And again here, since kinetic energy is not a function of position ever, it's a function of velocity. So instead of this, I can write it as partial derivative with respect to q of, let me write this properly, of L of t minus v. I can write it this way, right? Because again, t is not a function of q. So partial derivative of t with respect to q is 0. T is a function of q dot. And again, this is what? This is L. So I can write it as partial derivative of L with respect to q. So this guy here is partial derivative of L with respect to q. This is partial derivative of L with respect to q dot. And if I bring this term to the left-hand side and make it negative, then I have my final form of the Lagrangian method. Look at that. It's d over dt of partial derivative of L with respect to q dot minus the conservative force, which is partial derivative of L with respect to q, is equal to non-conservative force. And here, instead of showing it with F, I'm showing it with capital Q. So this capital Q is that non-conservative force. Okay, so again, here, this term is like mass times acceleration. This is the conservative force, and this is the non-conservative force. So this is equivalent, very, very similar to the second law of Newton, but written in terms of L, and L is an energy term, kinetic minus potential. But as I said, this method is not 100% energy, because on the right-hand side, you have a force term, okay, which you have to include. And we'll talk about it. Again, it's not conservative force. Now you might say, what is it about this Q and Q dot? And why don't we call them X and X dot and this one F? Why should we have changing notations? Well, the thing is, first of all, in many systems, the coordinates we use to describe the degrees of freedom of the system are not necessarily called X, right? So if you are moving horizontally, yeah, you might call it X, but if you move vertically, you might call them Y. If it's a pendulum, you might call it phi or theta. And there might be more than one. So here, Q represents basically any coordinate, any variable that describes the degrees of freedom of the system. Any coordinate, any variable that describes the free degrees of freedom of the system, the ones that are able to move them without any constraint, this is called Q. So Q here is called generalized coordinates. In some problems, we might have some selections for Q differently from the conventional selections, and I'll show you in a second. But this method will provide equations for those degrees of freedom in general, which now we call generalized coordinates, and here I underline them for you. So small qi is called generalized coordinate. The other thing is q dot, the time derivative of q's, we call them generalized velocity. So instead of x dot, we use q dot. And as I said, this qi, which is on the right-hand side of this Lagrange method, we call them generalized forces. We call them generalized forces. But just note that when we say generalized forces, yes, they are. The only thing is these are the forces that are not conservative forces, because the conservative ones will show themselves here. So the right-hand side here is only the non-conservative forces, Q's. Okay? So here is just a simple intro to this method. And as I said, the best way to learn this method is first we do a bunch of examples, and then we'll come back and we get into more depth of this, okay? And as I said, my goal is not to make you expert in the Lagrange method, because this is advanced dynamics, but I thought it would be good if you learn this alternative derivation of equations of motion, which is used in many applications in real-life engineering, before you get out of this course. So let me go over a few more examples and use this formula several times, and then I can talk about more terms. Okay, so this was a simple example, the mass spring damper system. Even with external force, you saw that I could easily get the equation of motion. Now we need to talk about a couple of other things. So one example in the text is the pendulum. So if you have a pendulum here with length L, with this angle from the vertical direction theta, and here you have this mass m. So now if somebody says, what's the equation of motion of this pendulum in general for any angle theta? And here we assume there is no friction, there is no torque, nothing. So it's just a pendulum on its own. So what is it? So one way that you know is I draw the free body diagram of this mass, which is T tension and mg. And we have done it. And then we take moments about this point O. And then you'll see that the equation of motion, if you remember, was theta double dot plus g over L sine theta equals 0, right? So we have derived this. It's nothing new. But now we're going to go into this new method. And again here, this L might be confused with the Lagrangian L. So your text here, this text that I gave you, called it D, and I can call it D2 or anything else. So if you don't mind, let me call it D to the length of the chord to avoid confusing it with the Lagrangian. So what's the Lagrangian here? Lagrangian is kinetic energy minus potential energy. And what is kinetic energy? Kinetic energy is 1/2 mv squared. Kinetic energy is what? It depends on where you set the datum. And here we set the datum at the pivot point. So this is the datum of potential energy. Therefore, this height here, this height, whatever it is, h, is below the datum. So the potential energy is going to be what? Negative mgh, correct? It's negative because it's below the datum. So this is my Lagrangian. Now, you need to relate the Lagrangian to this variable using which you describe the degree of freedom of the system, theta. So here, for you, your generalized coordinate q is the same as what? Theta, the variable using which you are describing the motion of the system. The system has 1 degree of freedom. Remember, this system, the degree of freedom is what? 1. And that 1 degree of freedom is what? Theta, which now we call it generalized coordinate. And the derivative of that is, of course, what? Theta dot or omega. So now, if I continue, the question is, how do I relate the velocity of the pendulum to theta or theta dot and this height to theta and theta dot? Well, what is velocity? If a mass point is rotating about a fixed point with angular velocity of theta dot, right? Because this is theta and this angular velocity is theta dot. And the distance from the point to the center is d, so you know velocity of this object, if we call this velocity, the velocity at any point, and it's perpendicular to the chord, it is equal to what? R omega, right? So it's d theta dot. Right? That's the velocity of the object. So you write it as 1/2 m times d theta dot, the whole thing squared, and then plus mgh. And this d here is not derivative. That's why, again, your text is using capital D. Let me use actually a different notation, because I'm not really a fan of that too, because you might say, well, what am I taking derivative or differential from? So let me use a different notation for length. And that's a good thing. Let me see. What parameter? A. How about A? A is better. So it is A theta dot. There we go. A is better. So here. A theta dot squared. And what is this H? H is related to A and theta, right? It's simply what? A times cosine of theta. So it is going to be mgh times A cosine of theta. So this is my Lagrangian. Now, is there any non-conservative force acting on this mass as it goes back and forth that is doing some work and we have to consider? Remember that when you have this mass, there are 2 forces acting on it, mg and h, and t, sorry, the tension. And mg, the work of mg is considered in the second term of Lagrange method. So it is considered here. Mg will show itself here, so we don't have to worry about mg. It's only this non-conservative. And there is a non-conservative force tension here, but as you know, and we have discussed it, this tension does not do any work on this mass as it moves. So there is no term associated with that that I need to use here on this right-hand side. So I'm good to go. So now, if I take those partial derivatives, what is partial derivative of L with respect to theta dot? So we go here, that to cancel, you get ma squared theta dot. And then what is the partial derivative of L with respect to theta, the general coordinate? As you can see from here, it is negative mga sine theta. Correct? So now I use that equation here. d over dt of partial derivative of L with respect to q dot minus partial derivative of L with respect to q is the non-conservative force, which in this case it is 0. So if I write my equation, it is going to be d over dt of this term minus this term is equal to 0, this one. And let's simplify. So 1m cancels from both sides, 1a cancels. And we can, this 2 both cancel. So you will get what? And if you want, you can actually divide by a squared. So let me divide by a squared. So here is going to be over a. So this is going to be d over dt of theta dot, which is what? Theta double dot, correct? And this is going to be g over a sine theta. Or g over L, if L is the length of the pendulum, is equal to 0. And you know, this was the equation of motion we found in the past using the Newton's method, right? Theta double dot equals negative g over L sine theta. That's the same thing here. Right? So it gives me the equation of motion also, this method. Again, this method does not show its power a lot here when I only have 1 degree of freedom and not too many reaction forces. But I'll show you later when we go to double pendulum, this is going to reduce my workload a lot better and make my life much easier. Right? So now, let's see. Some of you might ask this important question. Hopefully you do. That if I look at the same problem again, but instead of describing the degree of freedom of the system using theta, which is the most obvious one, I use redundant coordinates. So you know, this system has 1 degree of freedom, so ideally I only need what? 1 coordinate, 1 variable to describe the motion of the system, which is theta here. Some people might choose redundant variables, like what? Some people might say, well, if I choose the system and go instead of the polar coordinate theta, I choose the x and y, the Cartesian coordinates, right? How about that? So the position of this pendulum at any point, I call it y, and this position I call it x. And I want to describe the motion of the pendulum using x and y of the mass instead of the angle. So they say QIs, I have 2 QIs, are x and y. Okay, so I have redundant coordinates. How are they redundant? They are related to each other, right? They are not independent. You know that x squared, in this case, your x squared plus y squared is equal to what? Equal to a squared, correct? The length of the pendulum. So they are redundant. There is a constraint equation between them. If that's the case here, and I say that the velocity of this object at any point is, it has an x dot component in the x direction and a y dot component in the y direction, correct? So the resultant of which is the velocity of the pendulum. Can I still use this method of Lagrange and find the equations of motion for the system based on x and y, not based on theta? So I'm not going to use theta. Can I? Well, let's see. So the Lagrangian L is T minus V. So let's first find T and V. So T is kinetic energy, 1/2 mv squared. And for V squared, I have to say x dot squared plus y dot squared. Right, that's the magnitude of the velocity squared. And potential energy V is basically, in this case, negative mgy, correct? Right? because this coordinate is y and it's down, so it's negative mgy if, again, I assume this is my datum. So L is the difference between the two. And now, again, there is no other force other than mg, and mg is showing itself here. So the tension does not do anything. So all I need in this case is to use this. Qi non-conservative. So now I have to write this equation twice for I equal 1 and 2. And when I is 1, I have to use x. When I is 2, I have to use y. Right? So basically, I have to write these equations. And you know that the non-conservative is 0 in this case. So I have to write this equation. Correct? And to be consistent, let me make sure I write y the same all over the place. Like that. So now what do we get? We get d over dt of, what's the derivative of Lagrangian partial with respect to x dot? It is mx dot. Lagrangian does not have any x term, so this is 0. And then with respect to y dot, you have my dot. And with respect to y, you have mg, correct? And you get this. Now, is that correct? Let's take a look. So what do I get? Well, I get that here that the mx dot term does not change. And actually this is y dot. And the y dot term does change. And again, remember that x and y are not independent. They are related by this rule here. So if I want to describe the motion of the system, these two describe how x dot and y dot are changing, but x and y are not independent from each other. You have to include this guy as well. When you know x, you can find y from this equation and vice versa. Or if you basically from here take a time derivative, let's take a time derivative, see what happens. So you will get 2x dot plus 2y dot is equal to 0 because a squared is constant. So you see x dot and y dot are related using x and y, right? So again, although I have two equations of motion, but I need to combine them into one by relating x dot and y dot to each other, right? So from here, now the only thing is this part here, is this correct? is d over dt of my dot equals, so what is this? Let me first ask you, what is this? It looks like what to you? Where the x dot term, because m is constant, so the x dot term doesn't change. The y dot term changes due to mg. Now here, this is wrong. This sign is wrong. It should be positive instead of negative. Why is that? That's because of the way that we define y. So when we define y upward and this pendulum is downward and we define the potential energy negative mgy, well, at the moment, the y of the object is this. This is y, and this is x. The y is already negative as long as the pendulum stays below the x-axis. The y is already negative. And the potential energy is negative because it's below datum. So when y is negative and potential energy is negative, means potential energy and y have the same sign. If they have the same sign, I should not say v is negative mgy, I should say it's positive mgy. Because y is negative itself, it makes this whole thing negative. So here, this guy has to be what? Negative then? And so here, this makes this guy positive. And so again, if I rewrite this, let me ask the question again. If I write it, it would be like x dot equals constant, correct? Because derivative of that is 0 and m is constant. And then if I cancel the m terms here, it is going to be y double dot equals negative g. What does it look like to you? Have you seen this guy anywhere? Yeah, you might say that is what? That is projectile motion. You're right. In projectile motion, when there is no air drag, that's the equation of motion, right? X dot is equal to a constant, y double dot equals negative g, right? That's the projectile. So does the pendulum have the same thing as projectile? No. Why? Because in projectile, x and y are independent. The ball, when it's in projectile motion, it really has 2 degrees of freedom, x and y. And x and y are independent from each other. But in here, this pendulum is not free to move in any way it wants. X and y are constrained through this constraint equation. So it's not like x dot and y dot are completely free to change the way they want or be any number they want. They are related here. Okay, so what does that mean? It means that, well, fine, y dot changes as a function of g. So from here, if y double dot is negative g, then y dot is going to be like negative g times t plus y dot at time 0. Okay? And this x dot is constant, but now this x dot constant, whatever you want to call it, let's call it c, that c is related to this guy here through the constraint equation. So this c is not really an arbitrary constant. Okay, so you get 2 equations, but again, these 2 equations are not totally independent. They are related. They are constrained here by this guy. So if you plug it in, you will get, and cancel out the 2's, you will get x times that constant c plus y times negative gt plus y dot at 0 is equal to 0. So you see at any point, and x and y are related too. X and y are related too. Because x and y, from here, you can see that x is a squared over y squared, square root of that. So you can make it like this. and reduce it down to one equation only based on y and y dot, which does not look too nice. Okay, so now this is the equation of motion only based on y, and I got rid of the constraint, eliminated that, because I had 2 degrees of freedom that I shouldn't have in the first place. So the good choice, the good advice is, whenever you are dealing with generalized coordinates and you have constraints, make sure to get rid of the constraint and choose your generalized coordinates only sufficient to describe all the degrees of freedom that are independent. And it is mentioned here for you. Look at that. It says if there are constraints in the system, then there are fewer q variables than x variables. So in this case, by x variable here means everything that you chose. So in this case, x variable means both x and y. And q means what you should choose to describe the motion of this pendulum, which in this case is actually theta. So it says, yes, there are 2 variables, x and y, but q, that is theta, is only 1. So there are fewer q's than x's. Okay, so that's important. Choose your q's, choose your generalized coordinate in a way to avoid what? Constraints. Okay, so that's one of the important things about choosing generalized coordinate. Try to make them independent from each other. The other thing I have here is holonomic constraint and non-holonomic constraint, which I am not sure if I want to get into that, but it says if there are constraints, they are like this. And what does that mean? Means those parameters that you chose to describe the motion of the system, they are related to the generalized coordinates by simple functions directly. What does that mean? Well, in this case, I'm relating x and y, these x variables in general, the variables that I chose in this case, to the qi that I should have been chosen, theta. They are easily related to each other, so we can say that x is what? A sine theta, and y is a cosine theta. So you can say this is like f of theta, negative a, and this is like g of theta. They can even involve time if you want to. So you see there is a simple relation between the constraint coordinates and the generalized coordinates. Now, this is called holonomic, and I say an easy as simple. What does that mean? If a constraint described in terms of the coordinates themselves, we call it holonomic. So what is non-holonomic? Non-holonomic is when the constraint is described in terms of the velocities. So instead of being able to directly say x is related to theta, like in this case, correct? If instead of this, I have to describe my constraints into something like this. X dot equals to some function of theta dot, and y dot is equal to another function of theta dot. And I could not integrate these constraints. So these are my constraints. I could not integrate my constraints with respect to time and get them back to these simple equations between the x, y, and theta themselves. So can I integrate these equations with respect to time and get these guys? If I can do this integration, then I have no problem. I call it holonomic constraint. If I cannot integrate, if I cannot integrate these velocity constraints and write them in terms of position or generalized coordinate constraints, if I cannot do that and do this integration, then I call this constraint non-holonomic. And this is holonomic. So holonomic means in terms of the coordinates themselves. Non-holonomic means in terms of velocities, which I cannot integrate back and write in terms of the coordinates. Okay, and I don't want to get into more depth of that because, again, it goes back to advanced dynamics and it is beyond the level of this course. But since this notion was mentioned here, I just wanted to very fast refer to this holonomic constraint thing for you. Now, let's go over one more example which shows the real advantage of this method. So this example is the double pendulum, for which the equations of motion are not, if you want to go with the Newton method, they are not as simple. Why? Because I need to include the T forces, T1 and T2, in order to get the equations of motion. So here, you know, the system has 2 degrees of freedom, theta and phi, or you can call them theta 1 and theta 2. And as I said, when you draw the free body diagrams, you have M1G, M2G. Now in this case, both are M, so MG, MG. And then T1 and T2, and those T would include themselves, both of them are known, into the governing equations. So when you write the governing equations, you have to write include T1 and T2, and so your equations that you need to now solve for in order to get equations for theta double dot and phi double dot are going to be 4 equations instead of 2, where you have to eliminate T1 and T2 from those 4 equations, reduce it down to a 2 by 2, 2 equations and 2 unknowns, theta double dot and phi double dot. But with this Lagrangian method, I'll show you in a second that you do not need to bring in T1 and T2, okay? And you can just get rid of them. So in the case of this example here, again, what I need to do is to formulate the Lagrangian, right? So if I come here, and for my Lagrangian, so let's look at each one of them. So here, the velocity of this first pendulum here, V, or I can call it V1 if you want. I need to find that. How much is it? You know, since this object is rotating about a fixed point, the velocity of that, if you call the length of this pendulum and this one both d, it is going to be 1/2, or no, d, the velocity is, sorry, d times the angular velocity phi dot. So that's the velocity of this one. Now for this case, the velocity of this object is not as simple as d times theta dot, because this object is not rotating about this fixed point. So velocity of that is velocity of this point plus the relative velocity. So I need to add them together to get V2, and V2 is not going to be perpendicular to this second pendulum. So how do I find it? So that text that you see found coordinates x2 and z2 in terms of d, this d, theta, and phi, and then took time derivative from that. And I can do that too, okay? Or I can use what we learned in rigid body kinematics and find the velocity of this point as well. So it is all up to us, right? As I said, again, this text that we have found coordinate x1 and z1. By the way it described the coordinate, this text, did not call it x and y, call it x and z is horizontal and x is vertical. So the way that the coordinate systems are described in this case is a little bit different than the conventional, but it doesn't matter. So here we call vertical x is x and horizontal z. So as I said, found x1 and z1 based on phi, correct? So you can say that x1 is simply d negative d times cosine of phi, and z1 is d times sine of phi. And then in a similar process, x2 is x1 plus or minus d cosine of theta. So it is negative d cosine phi minus d cosine theta, and z2 is d sine phi plus d sine theta. Okay, and then took time derivative from these to find x2 dot and z2 dot. And then using those, it found the velocity of particle 2. So x2 dot, if you take time derivative, it is clearly going to be d sine phi phi dot and plus d sine theta theta dot. And this is going to be d cosine phi phi dot plus d cosine theta theta dot. And velocity of this particle, whatever direction it has, so it is going to be this one plus some number in this direction. So let's say like that. If this is v2, then I can say v2 squared, or just the v2 if I want v2. But remember, in the potential energy, I need v2 squared. So let me directly calculate v2 squared. v2 squared is x2 dot squared plus z2 dot squared, which is going to be square of all of these guys. So if I square that and add them together, I will get, and they all share d squared. So let me take the d squared off from all of them. So this is going to be sine phi squared phi dot squared plus sine squared theta theta dot squared plus 2 times the product So this is the square of x dot, and then z dot is similar. It is going to be cosine squared phi dot squared plus cosine squared theta dot squared, and then plus 2 times everything multiplied together. So cosine phi dot cosine theta dot. Okay, so this is everything, and now we can simplify. How? So these guys does have phi dot squared. I can add them together, and then it's going to be phi dot squared times sine squared cosine squared. So some of them will simply be phi dot squared. I can do a similar thing to this one and this one. If I add them together, it is going to be theta dot squared. And these two guys, they share the 2 term and the phi dot theta dot term. So if I do it, it's going to be 2 theta dot phi dot times sine phi sine theta plus cosine phi cosine theta. So this is going to be like that. And if I want, I can even simplify this a little bit more if I want to, right? Based on trigonometry, if you know, this is basically cosine of theta minus phi. So my V2 squared, it is going to be d squared times theta dot squared plus phi dot squared plus 2 theta dot phi dot cosine of theta minus phi. This is V2 squared. And V1 is already given. If we want, we can use the square version of this, but I have them, and the potential energies I can find too. So now T2, the kinetic energy of particle 2, is 1/2 m V2 squared. So it is going to be m times this whole thing, correct? Divided by 2. So this is kinetic energy of particle 2. Kinetic energy of particle 1 is 1/2 m times V1 squared, which is going to be 1/2 m times d times phi dot, the whole thing squared, correct? So that's T1, and then if I want, I can bring this 2 out, doesn't matter. So this is the kinetic energy of particle 2, and then I need to find the potential energies. So potential energy V1, as you can see, it is negative if I assume here is datum. And since x1 and x2 are upwards, so it is going to be negative d times this, which is cosine of phi, so it's negative d cosine phi times mg. And for the second one, it is going to be negative mg times the z, which was d cosine phi, and then minus d cosine theta. Okay, so now L is the total kinetic energy, which is T1 plus T2, minus the total potential energy, which is V1 plus V2. Okay, so it is going to be 1/2 m d squared phi dot squared plus 1/2 m d squared times phi dot squared plus theta dot squared plus 2 theta dot phi dot cosine of theta minus phi So this is the total kinetic energy, and then minus potential energy. So I have to negate both of these terms. So mg d cosine phi. This is then minus mg d times cosine phi plus cosine theta. Okay, so that is my whole Lagrangian. If I want, I can simplify it a little bit more since I have two phi dot terms. So this is going to be md squared phi dot squared plus 1/2 md squared theta dot squared. That 2 and that 2 would cancel. You would get md squared phi dot theta dot cosine of theta minus phi. And then here you have mg cosine, another mg cosine, so it's going to be 2 mg cosine. And 1 mg cosine theta. Okay, so this is my Lagrangian in a little bit simpler version. Now I'm ready to write my equations, and remember that I do not have any force other than tensions and mg's. Mg's are showing themselves into the conservative forces, and the t's that are non-conservative are not doing anything, so I can just simply throw them away. So now if I write my equation for theta, it is going to be d over dt of partial derivative of L with respect to, sorry, let's do it first for phi, because phi is the first angle. And then minus partial derivative of L with respect to phi is the first non-conservative force, as I said, is 0 for phi. So it is going to be d over dt of, let's take partial derivative with respect to phi dot. So it's the first term, 2m d squared phi dot. And then phi dot again is this term here. So it is going to be the rest of it, md squared theta dot cosine of theta minus phi. And there is nothing else that has phi dot in it, so that's it. Then minus partial derivative with respect to phi. If you look where we have phi, we have 1 here and 1 here. So partial derivative of that, that's cosine of theta minus phi, so it's going to be negative sign. That negative comes out, so it's going to be positive. So md squared phi dot theta dot sine of theta minus phi, and then here is going to be negative. With the negative, it's going to be positive, so positive sine phi, 2mgd. This is equal 0. So now I need to take time derivatives. And if you look here, every term has a d in it. So to make life simpler, I get rid of 1d. The other thing, I guess every term has m in it, so let me get rid of m's. And this one has g, these do not, so we have to keep the rest. So if you do it now, you are going to get 2d phi double dot and then d, and then here you have several terms that have time derivatives, so you have to use the chain rule and the product rule. So there's going to be d derivative of first one times the second one, plus d times first one times the derivative of second one. And derivative of second one with respect to time is theta dot minus phi dot sine of theta minus phi with a negative sign, right? Because that's cosine, so this guy has to be changed into negative. So this is the derivative term, and then plus the rest of it, which is plus d phi dot theta dot sine of theta minus phi, and then plus 2g sine phi equals 0. And here, the phi double dot, theta double dot term are unique, but let's see if there is any term we can cancel out. If not, we can add them. Just want to make sure everything is in good shape before we do anything else. Okay. Yeah, this negative, I somehow turn it into positive here without any reason. You have to be extremely careful, okay? A simple change sign mistake can ruin your equations. So make sure you double check your work and make sure your work is the best result you can get, okay? I guess the rest of it is okay. So now if you look, this term here, when you multiply it, it's going to be negative d theta dot squared plus d theta dot phi dot sine theta minus phi, and this is minus d theta dot phi dot sine minus. So this term and this term would cancel out. And if you divide everything by a d as well, you can divide everything by a d if you want. So get rid of a d here, a d here, a d here, and then you have to divide this guy by a d. So then your equation is going to look a little better. So it is going to be like 2 phi dot plus theta dot cosine of theta minus phi. This is phi, not phi dot. Then minus theta dot squared sine of theta minus phi plus 2g sine phi over d is equal to 0. So this guy is going to be your first equation of motion. And call it equation 1. Okay, this is the first equation of motion. It has both variables in it. It is coupled. And the second one, you have to do everything here, but do it with theta dot. So the second one is going to be like this. So you write it for theta dot and theta. Again, there is no non-conservative force, so you're good to go. You have to take now derivative of Lagrangian with respect to theta dot, and this is Lagrangian. Partial derivative with respect to theta dot is simply md squared theta dot. And then there is another term here, so md squared phi dot. Cosine term. And then minus derivative with respect to theta of this guy. And you have one derivative here, one derivative there. So this derivative is going to be negative sine md squared. Negative sine md squared. And this here is going to be negative mgd sine theta. Equals 0. And so now you have to take time derivatives, and again let's simplify the best we can. So I simplify md squared from everything, so you have to divide this by d again. If you do it, you're gonna get theta double dot and then here you have some terms need to be multiplied. So first phi double dot, and then minus phi dot times theta dot minus phi dot times sine of theta minus phi. So this is the derivative, and then here you have positive phi dot theta dot sine theta minus phi, and positive g sine theta over d equals 0. And again here, if you look, this phi dot theta dot term here is negative phi dot theta dot sine. This is positive phi dot theta sine. So again, these two terms would cancel out. And so your ODE will be theta double dot plus phi dot double dot cosine of theta minus phi. Again, this is phi. And then here is going to be positive phi dot squared sine of theta minus phi, and then plus g sine theta over d is equal 0. And again, this is your second ODE. And call equation 2. So we have the two governing equations of motion that I need, both second order, both coupled, because theta double dot and phi double dot appear in both of them. And if you ever need to solve these, because they are completely nonlinear, the thing is, you have from these two equations, you have to solve for theta double dot and phi double dot in terms of everything else, so that in each resulting equation, only one of them appears. So one of them is only theta double dot in it, and the other one is only phi double dot in it. And now you can solve them using numerical methods. And if we go here and look at the last result, you see that has been done. So here they are solved for theta double dot and phi double dot. Each equation only contains one of them, and you would get 136 and 137 as the resulting equation. And it's not really hard, as I said. Just consider it to be like a set of 2 by 2 linear equations. So consider this to be one variable and this is another variable, and solve for it. Or if you want, another way to handle it is, let me show it to you. If you write it in matrix format, so if I want to write my equations 1 and 2 in matrix format, it is going to be a matrix times phi double dot and theta double dot is equal to another matrix, where here are the coefficients of theta double dot and phi double dot, which are 2 and cosine term. For the first one and for the second one, they are cosine term and 1. And then the right hand side, you have to take everything else to the right hand side, which are these two guys. So theta dot squared sine minus 2g. So here, that's one of the terms, correct? Of course, this has to be negative because you're taking it to the right hand side. And for the second one, it is going to be phi dot squared. So this theta dot squared, the other one is negative phi dot squared times the sine term again, then minus g sine theta divided by d. So now this is a 2 by 2. You can call this matrix A. You can call this vector x unknown, and you can call this vector b unknown. And then ax equal b, so you can now say x is A inverse times b. And if you do that by inversing this guy here, and everybody knows how to invert a 2 by 2 and doing some simplifications, you can find phi dot and phi double dot and theta double dot separately based on the rest of the stuff, which you can see here. This is the result of that. Okay, and as I said, in these two equations, no T1, no T2, the tensions in the ropes appeared. While if we went with the Newton method, we have to deal with the 4 by 4. So in addition to these equations, or similar to these equations, there were 2 more equations, and in all 4 equations, you would see lots of the terms. You would see phi dot terms, theta dot terms, double dot terms, T1 and T2 in most or all of the 4 equations. So instead of a 2 by 2, you had to first eliminate T1 and T2 in those equations. You had a 4 by 4. Then once you eliminate everything, you will be down to these 2 final equations. So it makes it a lot easier and make the system of equations, the final system of equations that you have to solve for, smaller. Okay, that's why this method is preferred in systems that are complicated, like robots, where they have several degrees of freedom. This method is absolutely preferred over the Newton's method. Okay, so as I said, I don't want to get into a lot more the detail of this, and deliberately I make this video one video instead of 2, so you do not need to watch the whole video for the 2 sessions we have in the syllabus. You can just watch over half of them for each one of the sessions, and the other, and then you should be good to go for more practice in the classroom. Okay, thank you so much for your attention. See you in the next lecture.